Hi, guys. So now that we've heard all the evidence that Alfred Wegener came up with to support his theory of continental drift, let's go into the evidence in a little more detail so I can be sure that you understand. So the four pieces of evidence are the obvious puzzle fit of the continents, the rock and mountain matching across continents, fossil matching across continents, and the paleoclimate evidence, right? Which is like one example is finding old tropical stuff in cold places, and of course, vice versa. So let's get to the first one. The apparent puzzle fit of the continents, right? The apparent puzzle fit of the continents kind of shows us, I think every kid notices this, right? The first time you really get a look at a map of the world, the first thing that you notice is how South America's east coast seems to fit perfectly into Africa's west coast, right? So that's the thing that got Wegener thinking too, right? So we see it, we think of it as kids, and Wegener thought of it too. So that's number one. That caused him to look more deeply into it. And then he found out about rock and mountain correlation, right? So I'm going to tell you a little story. So this is a picture from a place called Acadia National Park. It's only a few hours away from here. It's up in Maine. And a few years ago when we first got our camper, it was one of the places we really wanted to go to when we went. It was just absolutely stunningly beautiful. And I was totally dorking out looking at all the different rocks and the fact that like the forest just seemed to end on a cliff, like butt up against the ocean. It was super exciting for me. So we traipsed around there for several days and we ended up in a place called Schoodic Point, right? And there's a really cool like nature preserve learning center there. And I wanted to get out as far out onto the cliffs as I possibly could. So one day we were at a place called Schoodic Point, and Schoodic Point is very rocky and the ocean butts up against it. And there's like a big crack in the cliff caused by weathering and erosion where the ocean waves like come crashing in and the water splashes up. And I think they called it, I want to say it was called Thunder Hole, but I'm not 100% sure. It was several years ago. But as we were walking around on the cliffs, like all the cliffs seem to be like this kind of rock, right? You can kind of see what it looks like. And then all of a sudden, out of nowhere, as I was walking, I noticed like this massively wide stripe of black rock, almost like somebody like cracked open all of this rock and like stuck this slab of black rock in between. I thought it was so cool that I stood on it and I took a picture of it and I posted it on Instagram. So I'm going to show it to you. So here's the picture, right? And as I was standing on this black rock, now I want you to see how big it is. There's a person over here, right? As I was standing on this rock, I looked at John and I was like, I wonder what this is, like what it even looks like. And some lady overheard me and came over and she was like, oh, that's basalt, right? And I was like, oh, and that kind of got me thinking, it got me thinking because I knew that I had a piece of basalt at home in my rock collection. I'm going to show it to you. All right, can you guys see this? So this is called basalt. Now, what's cool about this rock is it came from a place I've only ever heard about. I've never actually been there, but my parents went to Ireland several years before this. And when they asked me, my mom and my stepdad, and when they asked me what I wanted them to bring back, I looked at my stepdad and I was like, this probably isn't allowed because it's like an international like wonder and heritage site probably, but I want a piece of the Giant's Causeway. So let me show you a picture of that. This is the Giant's Causeway. And what's epically cool about it, if you look at it, if you look closely, you'll see that the rocks are like hexagon-shaped columns, right? And they almost look artificial, like somebody made them, but they're not. This is actually the way the rock forms on this western coast, on this coastline of Ireland. And the reason it's called the Giant's Causeway, these are really enormous. And I wish there was a person standing here so you could see the perspective, but I don't have a person. But I want you to notice that this entire coastline, if you look close at the picture, is made up of these just columns of basalt that are hexagon shaped. And the legends were that these were like the steps that giants walked on, right, back in the day. And I had heard of it. And I was like, oh, if you go there, like, I want a piece of basalt. And my stepdad took this piece of basalt from Ireland and snuck it back home to the United States and gave it to me. And it's been sitting here in my house ever since. My own little piece of Ireland. And I have not been there yet. Someday, right? Someday. Now, I got to thinking, because I know like Maine's in one place on the United States and Ireland's in another place all the way in Europe on the other side of the Atlantic Ocean. And so I decided, like, let me poke around on the Google and find out, like, what's in between. Is anything even in between Maine and Ireland? So I looked, and it turns out there is a place that also has basalt. And that place is Nova Scotia. So I'm just noticing this odd stick, hammer, walking stick, something over here in this picture. I have no idea what that's from. But I looked it up and I said, I wonder if there's basalt in Nova Scotia. And when I Googled it, this was the picture I found. On the coast of the ocean, basalt in a place called Nova Scotia. Let's take it to the map. The map, okay? Here's a world map. Now, I don't know if you know this. World maps are very distorted because the world is a sphere. And when we try to make maps which are flat, we kind of lose some of the size matching of the continents. But this is the map we're all used to seeing, right? Now, watch this. This little star right here that I just put on the map is the coast of Maine, where I was standing when I saw that strip of basalt in the cliff as I faced the Atlantic Ocean, which is this big old body of water right here. Now, watch this. The next star that pops up is going to be Nova Scotia. Boing. You see that? Now that makes sense, right? Geologically, not that far apart. Maine, Nova Scotia, both have basalt on the coastline. Now watch this. That is the location of the Giant's Causeway in Ireland. And I can practically lay a ruler on the map and draw a line straight across and show that the basalt is present in the coastlines, on the coastlines in these three places. Now, if I slid this entire Western Hemisphere up against Europe and Africa, my South America apparently puzzle fit into Africa, but now there is also a rock correlation of basalt formations between Maine, Nova Scotia, and Ireland. My most favorite part about this whole thing was that it was something, I'm sure all the scientists know about it, but I saw and discovered from my own personal experience. And that's what being a citizen scientist is all about, right? That's us. Next, fossil correlation. Just like the basalt is found across coastlines, opposing coastlines, so are fossils, right? Here's some examples. Amphibious fossils found on opposing coastlines, Plateosaurus fossils, Phytosaur, which kind of looks a little bit like an alligator, and Rhynchosaur, which kind of looks like a T-Rex walking on all fours, right? Now, I don't know how big these things are. I didn't go through and do all this dinosaur research, but I do know that these are 4 types of fossils, which help support the theory of continental drift because they were found exactly the same with very little adaptations for space on coastlines that are now across the oceans from each other. Remember this key. You're going to use it in a little bit. Finally, we have something called Paleo climate data. Paleo climate data, which is what we heard from the video, something about coal, which forms in warm places, but now we find it in places that are cold. And then there's other stuff that forms in cold places, but now we're finding it close to the equator that's hot. And that's a whole lot of thing. And either you get it or you're just like, yeah, whatever, I'll remember the other three things. Think of it this way. We live in northern New York. It gets really cold here and we get lots of snow. But imagine we started digging. Imagine we started digging in the ground and found, I don't know, a whole bunch of coconuts deep down underneath where we live. Now, don't forget, because of the law of superposition and how sediment and stuff gets stored in the layers of the earth, we know that the deeper you dig in undisturbed lithosphere, the older it gets. So it could be feasible that if I found coconuts, I don't know, dozens of feet under where I'm standing right now, that would safely say that there was some kind of tropical happenings going on here tens of thousands, if not hundreds of thousands, if not millions of years ago. So I hope that helps kind of solidify all those ideas from the video for you. Just to review, the evidence that the continents have drifted from a once supercontinent known as Pangaea are the apparent puzzle fit of the continents, rock and mountain correlations, that's matching, right? Fossil correlations, and paleoclimate evidence. Now, on the next slide, I'm going to send you to a standalone Google assignment. It's a puzzle. It comes from the American Museum of Natural History. It's a single slide. It's got a key of land formations and fossil evidence that you're going to use to slide the 7 pieces together to see if you can model what scientists believe Pangaea looked like according to the evidence. I'll give you a hint. You do not have to rotate any of the pieces of the puzzle. They are all numbered 1 through 7. The numbers will be right side up, okay? And if I was you, I would start with basalt. Good luck.